Hey, AB Calculus, it is Mr. Canfield. Today we're going to look at 3 important theorems, but we'll see how far we get. So on the AP exam, these are 3 theorems that you can be required to name. So we do have to memorize what they are, what they do. The good news is they're pretty straightforward. And generally the way that this works is we're going to have some kind of setup. So because stuff, or because is the word that I'm choosing right now, you can, they're not looking for you to write a specific sentence, but they want to see, because I have this information here, by a certain theorem, so info, comma, by this theorem, conclusion. So the only way that we're going to be able to say one of these conclusions is to say, since I know this is true, I'm allowed to use this theorem that tells me that this is true. So that's a really important idea, that we have a setup. Then we are allowed to, I like to say, invoke the name of the theorem, because it's like, you can imagine some like wizard or something like, okay, I have to have the special stuff to invoke the, and you're summoning some kind of. So I play too many video games. Okay, and then you get your conclusion. So here we go. All right, the first theorem that we're going to talk about is called IVT. So this is called the intermediate value theorem. You are allowed to use the abbreviation IVT. You are not required to write intermediate value theorem. Generally, abbreviations are not okay. But we have certain standardized abbreviations in AP Calc that they've decided, okay, everyone can use these. So intermediate value theorem. Let's talk about the basic idea of intermediate value theorem, and then let's look at some examples. So here is your basic idea. Let's look at some curve. Also, by the way, I'm going to deviate basically completely from what Stu does here. So that means there's some really good notes here, and then hopefully my notes are, if you don't want to use his, you can use mine. Or if you want to use both and get kind of different textures of it, you can do that. So let's just picture some function like this, okay? And let's say that right here, at 2, we have the y value 3, okay? And then, let's say, over here at 10, we have the y value 5. So this is, if we call this f of x. So my question for you is, does f of x ever equal 4 between 2 and 10? Does the y value ever equal 4 between 2 and 10? And your gut reaction should be, yeah, duh. It goes swoop, and it starts at 3 and it ends at 5. 4 is in between. It has to. Yeah, it has to be. It has to. Why are you asking me this question? This is a strange question. Yes, that's exactly right, and that is intermediate value theorem in a nutshell. So to put it a little bit more, let's start to get a little bit more mathematical. Every y value between 2 points has to happen. Every single y value. So here's maybe the question that you are expecting, you might expect from here. So when does it equal 4? I don't care. Intermediate value theorem does not care when it happens specifically, it just cares that it happens. And that makes this something special. This makes this called an existence theorem. And once you get out of high school math and you start getting into college level math and different things like that, existence theorems are really, really big, because the whole idea of mathematics is to be able to prove that something's true, or to be able to show that something's true. So, you know, that's like saying, okay, let's say 4, there's something special about 4, and I don't know what that special thing is, but we're able to say now f of x has to be 4 at some point. So f of x has to be this special thing at some point. And I don't know exactly where it is, but I know that it is. And that's, so existence theorems just say, so it exists. Okay, so what lets us say this? Because I drew a specific example where it's obviously going to be 4. Let's look at a different example that kind of shows the prerequisites to be able to use the intermediate value theorem. To be able, so, because you might just say, well, look, every function ever, it's just going to pass through all the y values between 2 different y values. Like, I don't need a theorem to say that. Yes, you do. Because what if instead, you know, all things equal, 3, 5, just a little bit smaller of a picture. Let's say we're here, but our function looks like this. All right. So now, does my function equal 4 at some point? And you might be like, well, if this is 4, yeah, it's gonna be like, you know, it's gonna be like right there. No, it's even gonna be right there again, yeah. So, okay, great. So that wasn't a problem, Mr. Canfield. What are you getting at? Okay, well, let's say we had a slightly different problem. Again, all things equal, so. Let's say we did this now. Now, does the function ever equal 4? And if I drew, as long as I drew it right, yeah, no, it doesn't equal 4. So here's the problem. Just because I start at 3 and I end at 5 doesn't mean I pass through 4. The only way that I can say I definitely pass through 4 is if our function never breaks like this. And if you remember from a previous unit, that's called if the function is continuous. So let's go look at the fancy language here and see what's going on. So it says, suppose that f of x is continuous on an interval. So this is an interval a to b, and that's all that means. So I know some of you don't like interval notation. When I do intervals, so he's using a closed interval here. That's a less than or equal to x less than or equal to b. In this class, you will always be allowed to just use, we can use what's called an open interval whenever we're talking about intervals. So suppose that f of x is continuous on an interval from a to b. Let m be any value between f of a and f of b. Realize f of a, you know, that's that first y value. In our case, that was the 3. And then f of b is the second y value, that was the 5. And m is some value in between. In our case, m was 4. Then there exists, all right, I want to show you a fun symbol. I do mean this is a fun symbol. There exists. It's a shorthand symbol that you use in taking notes. It helps you save writing. Instead of writing there exists, we see this so often in math that a symbol was invented. It's a backwards E. If you ever write, so there exists, so, you know, think about this. I'm trying to write notes quickly. I'd be like, suppose f is continuous on a, b, there exists, so then there exists, I'm writing in a backwards E. I use this in notes all over the place. Once I learned that, I learned a few symbols in college, and it's just fun to have little abbreviation symbols because my notes are just for me. You will never have to do this. I will never use this in a formal paper for you guys. I'm never going to formally ask you to do this. It's really, really helpful for your own personal notes and edification, though, so I wanted to show you. All right. Then there exists a number C so two things happen. This first thing says that C is between A and B, and then it says that f of C is equal to M. So in our situation here, it's saying C is somewhere between A and B, and that C is equal to 4. Oh, wait. So for us, A was 2, B was 10, right? On our graph that we looked at. So the question that you might get is, does f of x ever equal 4 on the interval from 2 to 10? And you could say, since, or you can spell since wrong, so since f of x is continuous now, with a problem like this, you would actually, if they didn't give you the function, they'd be like BTW fam f of x is continuous, smiley face. So they would let you know that f of x is continuous, or it's going to be like a polynomial, or it's going to be something where we can show, hey, this is continuous. So since f of x is continuous, and I only care that it's continuous on 2 to 10. Now here's the thing. A lot of people say, well, since it's continuous, we have a y value of 4 between those because we start out at 3 and we end at 5. No. I'm not allowed to say that the y value is 4. IVT lets me say that the y value is 4. So since f of x is continuous on 2 to 10, by IVT, there, now I can say whatever I want. Let's see, by IVT, I'm going to be able to say that there exists C on 2 to 10 You know what? I think I'm missing something. I'll just tack it on at the end. We didn't talk about, and we start out at 3 and we end at 5. We should mention that too. There exists C on 2 to 10. Oh, here's another one. Such that. A nice abbreviation for such that is ST. This is another very common one. You see that in math textbooks even. They'll write ST because you write such that so often. Such that, and I could say f of C equals 4 because f of 2 is less than 4, which is less than f of 10. That would be one way to be like, because 4 is between the two y values. I could have said it earlier, since f of x is continuous on 2 to 10, and f of 2 is less than 4, which is less than 10. You generally want to say something about how the two y values are below and above. And let's get what we're like. Let me explain why we are being so annoyingly complicated with this. When somebody reads your paper, they are not allowed to assume that you know anything, okay? So if you said, yeah, it equals 4, as far as I know, you didn't even look at the picture, you just decided to say, yeah, it equals 4. We basically have to it's almost like we're the bully and we're making a kid give us their lunch money. Like we have to take away every option. Like, give me your lunch money, give me those points. I need those points. And the only way that we're gonna get those points, because they're not just gonna give up those points. The only way they're gonna give those points is if we give them, look, there's all this info, okay? Look, the info that I have, I know that my 2 y values are below and above 4, and you could probably even say that. You don't maybe need to write it as fancy as I tried to write it. And then you got to give me points for naming the theorem that I'm naming there. I named the theorem, and then I showed the conclusion that that worked. So when I give test questions like this, generally what I'm going to do is I'm going to ask you a question kind of like this, and I'm really just expecting that you're going to show me that you understand that it starts out, and it could have been, it could have been the other way. It could have been like this. The big idea, though, is that you're showing me that the 2 y values, and there's this interval, and there's the continuous function. So you set up, name the theorem, knock it down. All right. He's going to talk about it a little bit differently. That's great. So let's keep going and do some of these examples. All right. Show that this is off of the screen. All right. I need to show that f of x is equal to 2x cubed minus 8x squared plus 5x minus 2 has at least one root between x equals -1 and 4. So that's -1 to 4. So I'm just going to oh my goodness, I forgot an important word to say here. How many times does f of x hit 4? When you see the picture, well, yeah, it hits 4 once. But what if it had done this? Now it potentially hits 4 more than one time. So instead of saying there exists c, if we want to be really precise, we should say at least one c. So IVT, not only does it say, yeah, that 4 happens somewhere where, it's somewhere between those two, I don't know. Not only does it say it, that's all it can say, beyond that, it can also only say, it happens at least one time. It could happen more. I don't really know how many times it happens. I don't care, I know it happens once. All right, and then after this one, I'll give you, maybe I'll give you a real life example that, oh, wait, no, that's more of a MVT. That's a little bit later. Okay, so I want to show it has at least one root. Wait, this is asking, what? At least one root. That's a teacher leading thinking right now. Wait, one root. Oh, roots are when y is equal to 0. So since it's asking me to show that this has at least one root, it's really saying, look at f of -1. Look at f of 4. Is one of these above 0 and then one of these below 0? Because we're trying to show that this hits a y value of 0 somewhere between those two. So let me plug it in and figure it out. Yeah, I don't want to do this. I'm going to use a cheat code. All right, so I got negative 17 for f of negative 1. And then $18. So another way I could do this to, by the way, that's in case you missed it, I just did synthetic division, and the remainder is what you get when you plug it in. It's one of those things you learn in pre-calc. Oh boy, excuse me. Another thing we could do here, you know, do the graph and then go use the table. So negative 1, I got negative 17. 4, I got 18. So I thought I would show you this. If you're not comfortable doing synthetic division, then I wouldn't do it. But synthetic division is easier than actually plugging this in and doing the arithmetic. So, all right. Anyway, so you got the numbers however you got the numbers. And so now I can say, since f of x is, wait, how do I know f of x is continuous? Because I can't just be like, oh, I know it's continuous, because they didn't tell me, they just gave me this formula. Since f of x is a polynomial, it is continuous. And let's see, f of negative 1 is less than 0, which is less than f of 4. I don't need to actually say what they are. That's shown up here. This work is admissible in this problem. F of negative 1 is less than 0, which is less than 4. All right. I have my two necessary conditions to say that. So by IVT, there exists at least one C on negative 1 to 4 such that, that's how you spell that, right? Such that f of C is equal to 0. Let's see if I've said everything I need to say. Did I say it's continuous? Yes. Did I say my y value is between, yeah, yep. By IVT, there exists at least one C. I think I said everything. All right, let me show you what I would write for my own personal, instead of writing to my class, I would write, let's see, the polynomial f of x is continuous for all, oh, by the way, upside down A means for all. For all real numbers. Let's see, the polynomial is continuous for all real numbers. And f of negative 1 is less than 0, which is less than f of 4. I think I'd still say that the same way. Therefore, there's another one. 3 dots means therefore. or in conclusion, therefore, there exists C on -1 to 4. This is like as an element of or contained within it's a, what is that, sigma? It's not E, it's like this little like I think it's sigma, such that f of C is equal to 0. So not terribly shorter. Nope, I'm wrong. This would not get full credit. I didn't invoke the name of IVT. So I used to say, therefore, by IVT. Therefore, by IVT, there exists C on the interface. Yeah. So if you don't invoke the theorem, you're wrong. So IVT, one of our theorems right there. So example 2, half an hour in, we're only on example 2. It's worth going slow and talking about the language and making sure it makes sense. It'll let this take the time it needs to take. Does the IVT guarantee roots for this on 0 to pi? Let's see. So all I would really need to do here is, first I need to check, is it continuous? Yeah. How do I know it's continuous? Sines and cosines are part of that continuous family. You might remember that from the notes. Sines and cosines are continuous. And since it's just a string of them multiplied together, it's fine. And then 0 to pi. So I just need to plug in 0. And pi. And find out what we get. One of these should be a positive number, one of these should be a negative number. If I have that, then I know that if my y values are positive and negative, then there has to be a transfer. It has to go over 0 at some point. So let's see. It's 5 cosine of pi. Well, cosine of pi is -1, so that's -5. I wrote 3. Oh, that's 3 times 0, not 3 cosine. So sine of 0 is 0. So I got 0 for this one. Now cosine of 2 pi, that's 1, so that's 5. And sine of 3 pi, that's 0. Minus pi, I got negative pi. All right. So, did I do that right? That feels wrong. No, that's right. That's a little bit funky. Does it guarantee roots on this interval? Well, there's a root right there. So, yeah? I don't know. That's a weird question to ask. Yeah, the IVT guarantees it, but we don't even need IVT because I found a root. So, like, sure, we can use theorems to say, yes, this has to happen. I can also just use some evidence and go, here's some direct evidence. It happens. Generally, though, when we're doing these theorems, we're not trying to give the direct evidence of, yes, this happens. We're trying to say, or like, yes, here it is. We're trying to say, yes, we know that it occurs, and I don't care where it is. That's actually one of the things that I liked the most about math in college was I thought it was really funny that mathematicians go, yep, there's an answer. Where? I don't know. Let the physicists figure it out. I loved that, like, that attitude of, yeah, I know there's one, and I don't care what it is. And just a side note, there's lots of mathematics that cares exactly what the answer is. And we care a lot about what the answers are in this class. I had just never seen that perspective before. So it was really cool to see that that is a valid way to think about things. All right, so I actually want to just focus on IVT right now. I don't want to look at the other two theorems. I want to give each of them their own video. I think that's going to be better. So let's read through this, and just because I want to give you some practical stuff, even though IVT is one of the more obvious theorems that we do. So the intermediate value theorem has practical. Oh, did I explain why it's called the intermediate value theorem? It's a really common sense name. Intermediate, somewhere in between, value, number theorem. The somewhere in between number theorem. So 4 is our intermediate value. It's intermediate value between 3 and 5. Okay, the IVT has practical applications. For instance, if a car is going 40 miles per hour at some instant of time and needs to quickly stop, it will be traveling at every value between 0 miles per hour and 40 miles per hour in the time it takes to stop. So that means at some point it's going 23.6 miles per hour. It has to if it's going to go from 40 to a stop. You might have never really thought about that before, but and maybe you have. You have at one point in your life been 3'2", because you're taller than that now. And you started out when you were born, you were younger than that. You were shorter than that. It's guaranteed you were 2'6" at one point. Exactly 2.6. And then there's a place where you were 2 foot 6 inches and 0.3 inches on top of that. It might have only been for an instant, but it happened. Okay, let's see. Oh, that's what he talks about right there. I promise I wasn't looking at that. Maybe subconsciously I saw it. The IVT can fix a wobbly table. I don't believe you. If your table is wobbly because of an uneven floor, just rotate the table. Why? We can always have 3 legs on the ground. It is the 4th that is the trouble. Suppose the floor was like sand, so the leg could also go into the ground. If we rotate the table, at some point, oh, he got me. At some point, the 4th leg will be above the ground, and at another point, it will be below the ground. So by IVT, there has to be some point where the 4th leg perfectly touches the ground. If you've never tried this, I encourage you to try this. Another way to balance out tables is to use little pieces of wood or paper to prop up that 4th leg. If the orientation of your table is important to you. Okay, so next video we're going to talk about Rolle's theorem. But this is enough to do the first 3 homework problems. So I would try the first 3 homework problems and check them to see if it's making sense before you move on to Rolle's theorem, because Rolle's theorem is a completely different thing. We're just kind of lumping them all together here. So hope this is helpful. Bye.